All right, so today we're going to talk about conjugate pairs and how those conjugate pairs relates to roots of polynomials. So starting here, I've just got a few examples of complex numbers, irrational numbers. Now our irrational numbers are going to be these ones with square roots. Those are examples of irrational numbers. Our imaginary numbers are right here. Now as we combine a rational number, so in our first problem we've got this 2, so that 2 is a rational number plus the irrational square root 3, or when we're adding in the imaginary numbers we call that a complex number. Now what we mostly care about is recognizing that the rational number in these conjugate pairs is going to stay the same, so 2, and then the sign on our irrational number or on our imaginary, that's going to change. So rather than 2 plus square root 3, we have 2 minus square root 3. Rather than 3 minus square root 5, we'll also have 3 plus square root 5. 2 minus 5i, 6 plus 3i. And since that was just a positive square root 7, we now have negative square root 7, or a positive 3i. Each of these is an example of a conjugate pair. All right, so these aren't too hard to write or to figure out. Once you've got them, you just change the irrational or the imaginary number. You change the sign on it. Now, what's interesting about these conjugate pairs is that if one of them is a root, then the other is a root as well. Now that's working both with these imaginary numbers and the irrational numbers. All right, so if we know one, then we know the other also has to be a root. So if I were to say in this problem right here that 3 minus the square root of 5 is a root of my equation, then I also already know that 3 plus square root 5 is also a root of my polynomial. So let's look at one of the ways that this is useful. Now I've already given some of the conjugate pairs already, so let's try and figure out what the polynomial based off of these conjugate pairs is going to be. Now if I had something kind of simple, if I knew that I had roots at x equals 1, at x equals a 3, and at x equals negative 1, then writing out my polynomial in factored form is fairly easy. I do x minus the 1, x minus the 3, and then x, I could put x minus negative 1, but minusing a negative turns into plus. And so relatively easy. Now that's if we're doing all rational numbers. It really isn't that different if we are using the irrational numbers. So I have x minus the 3i and x minus negative 3i. So that turns into our plus that we see right there. Okay, now I've written that out. Now I don't want to be dealing with these imaginary numbers, so I'm going to go ahead and multiply through and get myself to standard form. So as I start to multiply through, I get x squared plus a 3xi minus 3xi, and then minus 9i squared. Okay, well this isn't too bad. I can simplify that. First I got x squared, no other x squared, so we'll leave it like that. 3xi minus 3xi, well that's just 0. And then a minus 9i squared. Now an I squared is a negative 1, so that is essentially negative 9 times negative 1, which is positive 9. So x squared plus 9, we just found our answer, x squared plus 9. All right, so now let's try this next one. Similar thing. I'm going to start off with writing my x minus square root 7. Multiply that by x minus a negative square root 7, so x plus square root 7. And now we're just going to multiply that through. So x squared plus square root 7x minus square root 7x minus square root of 49. All right, so simplifying that out, we're going to have x squared now positive 7 square root 7x minus square root 7x, just a 0, and then minus square root of 49 is a 7. And there we go. That is the standard form that would have those two factors. That would have the factors square root 7 and negative square root 7 for its zeros. All right, so let's do this once more. We've got a bit more of a complex number. So not just an imaginary, not just an irrational, but a complex number because we've got our rational plus our imaginary. We start out pretty much that same way. So we've got x minus, and now our first one would be a 2 plus 8i. And then we've got x minus its conjugate pair, which would be 2 minus 8i. So x minus 2 minus 8i. Now we can make that simpler by distributing through that minus. So this will turn into x minus 2 minus 8i, and then x minus 2 plus the 8i. All right, so now I've got my two factors. I need to multiply them together. I'm going to go ahead and use a lattice to multiply all of these together just to help me out. Helps me to organize my thoughts. You can just do this using a good long distributive property, but I find that writing it out with all of these boxes helps me to keep it organized. So x times x is going to be x squared, negative 2x, and then negative 8xi. Negative 2x, negative 2 times 2 is 4, positive 16i. All right, now 8xi, negative 16i, and negative 64i squared. All right, so now to take all of that, one thing I do notice, I've got a 8xi and a negative 8xi. Well, that'll be 0. Negative 16i and positive 16i. Those will be 0. And my negative 64i squared, well, I squared is negative 1. Negative 1 times negative 64 means that one is just going to turn into positive 64. So now I'm ready to write this out. We've got x squared minus 4x's. And then we got a plus 4 and plus a 64, so plus 68. And there you go. We have our standard form for a polynomial that would have the roots 2 plus 8i and 2 minus 8i. All right, now this is us finding what that polynomial form would be. What if we have the polynomial and we know one of the zeros, and what we actually care about is finding the factored form, because the factored form tells us so much about the zeros, and that can be so much more helpful. So first thing we're going to do is find the polynomial of the complex root. Now that is what we've already been doing. Step 2, we're going to divide the original polynomial by the polynomial of the complex root. Then for our step 3, we're going to write it out in its factored form using the two factors we'll have found. And then finally in step 4, we're going to factor out the remaining factor if it's possible. All right, so let's start out with finding the polynomial of the complex root. Here's my complex numbers, so its conjugate pair is going to be 2 minus 4i. So they're going to be my 2 that I'm going to start with. So we've got x minus the 2 plus 4i multiplied by the x minus 2 minus 4i. Go ahead and distribute through that minus, so minus 2 minus 4i, and then x minus 2 plus 4i. All right, so now just to multiply that through, we'll have x minus 2 and a negative 4i, an x, a negative 2, and a positive 4i. So once again, I just like to use this box when I'm going to be multiplying a lot of these together. Makes it go a bit easier and faster. So x squared, negative 2x, negative 4xi, negative 2x, 4, 8i, 4xi, negative 8i, and negative 16i squared. All right, so now that I've got that, I know that my polynomial should be an x squared minus 4x. Now I've got that negative 16i squared, so negative 16 times by a negative 1, going to be positive 16, 16 plus 4 plus 20. So this was all of our work for that step 1. All right, so that's how we found the polynomial from the complex root. Okay, and that's our result right there. So now for step 2, I'm going to divide my original polynomial by the polynomial of that complex root. So I've got x squared minus 4x plus 20, and we are going to divide it by our original polynomial, x to the power 4 plus x cubed plus 4x squared plus 84x plus 80. That's a fun one. All right, so now we're just going to do this long division. Remember, when you're doing long division, you're focusing in on that leading term. So what times x squared gives me x to the power 4? Well, x squared. Now we multiply it by each of the numbers that we already have. So x squared times the 20 will now give us a 20x squared. All of that has to be subtracted. So I now get 5x cubed minus 16x squared. Drop down the next term, so the 84x. And repeat. So what times x squared gives me 5x squared, or 5x cubed, I should say. Well, 5x. So we'll get 5x cubed. Now 5x times the negative 4, negative 20x squared. And 5 times the 20 plus 100x. We're subtracting all of that. So 5x cubed minus 5x cubed is 0, negative 16x minus negative 20x. So we'll get 4x squared. 84x minus 100x, so a negative 16x. And drop down the 80. All right, final step. So what times the x squared gives me 4x squared? Well, that's a positive 4. So we'll have 4x squared minus 16x plus 80 works out so nicely that we have 0 remainder. All right, so that's our step 2, doing that long division. to find what our two-factored forms are. So now we've got our x squared minus 4x plus a 20, and we have that is multiplied by x squared plus a 5x plus a 4 and there we go. So this just came from how we divided. We got our first term here from our first step. Now for our final step, we can look at if there's any of these that we can factor even more. Now, this first one, I'm not going to be able to factor it more. I already know what its zeros are, and they're complex numbers. So that's as simple as it's going to get. However, this second one, it is possible that I might be able to factor that one out. So I can think about what multiplies together to give me a 4, but will add together to give me a 5. Take a moment to think about it. The answer is a 1 and a 4. All right, and so that was my final step, was taking that one polynomial that still could be factored into a smaller form and doing so. All right, so this is your lesson on working with conjugate pairs, and I hope it's helpful.